Welcome to our exploration of three fundamental statistical techniques: principal component analysis, exploratory factor analysis, and confirmatory factor analysis. Principal component analysis, or PCA, is a dimensionality reduction technique that finds orthogonal components capturing maximum variance in the data. Exploratory factor analysis, or EFA, aims to uncover underlying latent factors that explain observed variables without prior structural assumptions. Confirmatory factor analysis, or CFA, tests a hypothesized factor structure, allowing researchers to validate measurement models based on theory. Let's compare these three techniques. While they may seem similar, each serves a distinct purpose in statistical analysis. Understanding these differences helps researchers select the appropriate technique for their specific analytical needs. A scree plot is a crucial tool in principal component analysis for determining how many components to retain. In PCA, each principal component explains a certain percentage of the total variance in the data. The first component explains the most variance, followed by the second, and so on. A scree plot displays the eigenvalues or variance explained by each component in descending order. The key to using a scree plot is identifying what's called the elbow point. The elbow is the point where the plot sharply changes from a steep curve to a more gradual slope. Components to the left of this elbow point explain most of the variance in your data. Components to the right of the elbow explain relatively little additional variance, which means they may not be worth keeping in your analysis. Here's another example of a scree plot showing both the individual and cumulative variance explained by each principal component. When selecting components, researchers typically use multiple criteria. The Kaiser criterion keeps components with eigenvalues greater than 1. Another approach is to keep enough components to explain a set percentage of variance. The visual elbow method we discussed is often the most practical approach. Let's consider a practical example. Imagine you have data with 20 variables measured on 300 observations. The scree plot shows a clear elbow at the fourth component. These four components together explain 82% of the total variance in your dataset. In this case, you would likely retain just these first four principal components. Proper component selection through scree plot analysis offers several benefits. It effectively reduces dimensionality while preserving the most important information in your data. It helps eliminate noise from less important components. It makes subsequent analysis more computationally efficient, and it can help prevent overfitting when building predictive models. Extraction methods are crucial in exploratory factor analysis for identifying underlying factors. Let's compare two major extraction methods: principal component analysis and principal axis factoring. This diagram illustrates the fundamental conceptual difference between these approaches. PCA treats components as linear combinations of variables using total variance. PAF models variables as functions of latent factors, focusing on common variance. A key difference between these methods is how they treat variance. Total variance can be decomposed into common variance and unique variance. PCA analyzes the total variance, while PAF focuses specifically on common variance among variables. PF focuses on communality, which is the proportion of each variable's variance that can be explained by common factors. Principal axis factoring uses an iterative approach to estimate communalities. Statistical software like SPSS follows a multi-step process to achieve this. Principal axis factoring follows an iterative process to estimate communalities. It begins with initial estimates, then repeatedly refines them until convergence. The mathematical foundation of both methods relies on the principal axes theorem, which allows us to decompose a symmetric matrix into its eigenvalues and eigenvectors. When choosing between extraction methods, consider your research goals. PCA is useful for data reduction, while PAF is better for identifying latent constructs underlying your variables. Understanding these differences is essential for proper application of exploratory factor analysis.
Factor rotation is a critical step in exploratory factor analysis that helps us make sense of our results. After extracting factors, we often find that the initial solution is difficult to interpret. This is where rotation comes in. In an unrotated solution, variables often load on multiple factors, creating a messy pattern that's hard to interpret. The goal of rotation is to achieve simple structure, where each variable loads strongly on only one factor, making interpretation clearer. Factor rotation can be visualized as turning the factor axes to better align with clusters of variables. Here we can see how rotation transforms the coordinate system. Varimax is an orthogonal rotation method. It keeps factors at right angles, meaning they remain uncorrelated. It maximizes the variance of squared loadings for each factor. Oblimin, on the other hand, is an oblique rotation that allows factors to correlate. This often produces a more realistic representation in fields where constructs are known to be related. Your choice between these rotation methods should be guided by theory and research context. Use Varimax when you expect factors to be uncorrelated and Oblimin when relationships between factors are likely. Remember that rotation changes how we interpret the factors, but it doesn't affect the total variance explained or the communalities of the variables. It simply redistributes the variance to achieve a more interpretable solution.
Factor loadings are critical values in exploratory factor analysis that show how strongly each variable correlates with each underlying factor. When interpreting factor loadings, we assess the magnitude of each loading. Values above 0.70 are considered excellent indicators, while values below 0.32 are typically too weak to be meaningful. Let's examine a real example of factor loadings from a career aspirations study. Note how each item loads strongly on factor 1, with values ranging from 0.79 to 0.85. We can clearly see high loadings clustered under factor 1. These high values indicate these items are strongly related to the same underlying construct. To name factors, we examine the content of items with the highest loadings. This diagram shows how variables cluster around underlying factors. The factor naming process follows several key steps. First, identify items with high loadings. Then, carefully examine their content to identify common themes before assigning a meaningful label. Let's work through a concrete example. These 4 items all load strongly on the same factor. When we examine their content, we notice they all relate to having defined career plans and objectives. Based on these high-loading items, we might name this factor career planning and goal setting, since all items relate to having clear plans and objectives for one's career. Sometimes variables will load on multiple factors, creating what we call cross-loadings. Variable 3 in this matrix loads on both factor 1 and factor 2, which complicates interpretation. When interpreting factors, focus on items with loadings of 0.55 or higher. Strong factors should have at least 3 high-loading items. Always consider theoretical relevance alongside statistical values to ensure your interpretation makes conceptual sense. To summarize, factor loadings indicate the relationship between variables and factors. Focus on high-loading items to interpret and name factors. The name you choose should accurately reflect the underlying construct represented by those items. In confirmatory factor analysis, the measurement model specifies how observed variables are related to underlying latent constructs or factors. Path diagrams are visual representations of measurement models. Let's examine the key elements of these diagrams. Latent variables, or factors, are unobserved constructs represented by circles in path diagrams. Observed variables, or indicators, are directly measured and shown as squares or rectangles. Factor loadings are represented by straight arrows from factors to indicators, showing the strength of relationship. Covariances between factors are shown as curved double-headed arrows. Error terms represent unexplained variance in indicators and are typically shown as small circles. Here's a basic measurement model in CFA. A single latent factor, represented by this circle, influences 3 observed indicators, shown as squares. The arrows pointing from the factor to each indicator represent factor loadings, denoted by lambda. These loadings quantify how strongly each indicator reflects the factor. Each indicator also has an error term, represented by epsilon, which accounts for measurement error and other sources of unexplained variance. Now let's look at a more complex model with 2 factors. Each factor influences its own set of indicators. The arrows represent factor loadings, showing how each indicator is influenced by its respective factor. Different patterns of loadings allow us to test specific measurement hypotheses. The curved double-headed arrow between factors represents their covariance. This allows us to model the relationship between the latent constructs. Here's a practical example of a simple regression model specified in CFA. This path diagram shows a relationship between motivation and reading. In this model, motivation is the predictor variable with a variance of 99.8. The regression coefficient of 0.530 shows the strength of the relationship. The residual term with variance 71.766 represents unexplained variance in reading. When specifying a CFA measurement model, remember these key points. Define the number of factors based on theory. Specify which indicators load on which factors. Determine whether factors should covary. Set the scale by fixing a loading or factor variance, and account for measurement error in all indicators. Proper reporting of confirmatory factor analysis results is crucial for transparency and replication. When publishing CFA results, you should include several key components to ensure your readers fully understand your analysis. Factor loadings should be reported in a clear table. This example shows standardized loadings for 2 factors with dash marks indicating non-significant paths. Multiple fit indices should always be reported to provide a comprehensive assessment of model fit. Include thresholds and interpretations for clarity. Including a visual representation of your measurement model greatly enhances understanding. This diagram shows 2 latent factors with their observed indicators and error terms. When reporting CFA results, follow these best practices to ensure your research is transparent and reproducible. Here's how CFA results might appear in the methods section of a journal article. Notice the concise yet comprehensive reporting of all essential elements. By providing thorough documentation of your CFA process and results, you enable other researchers to evaluate and potentially replicate your findings. Cross-validation is a critical technique in statistical analysis that helps assess whether our models will generalize effectively to independent datasets. Why does cross-validation matter? It prevents overfitting to training data, ensures model reliability across different samples, provides a realistic estimate of model performance, and is essential for validating factor analysis and PCA solutions. One common approach is split sample validation. This technique involves randomly dividing your dataset into 2 portions: a training set, typically containing 70 to 80% of your data, and a testing set with the remaining 20 to 30%. The split sample validation process involves 3 key steps. First, develop your model using only the training data. Second, test this model on the held-out testing data. Third, compare performance between the samples to assess consistency. Here's an example of split sample validation results using ANOVA tables. Notice how both samples show statistically significant relationships between the predictors and dependent variable, indicating that the model generalizes well across different data subsets. Another powerful approach is k-fold cross-validation. This method divides your data into k-equal subsets or folds. Each fold serves as a testing set once, while the remaining folds collectively serve as the training set. The process is repeated k times, with each iteration using a different fold as the test set. This approach provides a more robust validation by utilizing all data for both training and testing. Cross-validation plays a crucial role in preventing overfitting, which occurs when a model performs well on training data but poorly on new data. On the left, we see an overfit model that follows the training data too closely. On the right, a balanced model that will generalize better to new data. Here are some key recommendations for implementing cross-validation. For smaller datasets, use k-fold validation with k equal to 5 or 10. For larger datasets, split sample validation may be sufficient. Always report your cross-validation performance metrics, and make sure to validate factor structures across your different samples. Financial markets generate vast amounts of data across multiple currencies, stocks, and economic indicators. For example, consider these 5 currency exchange rates against the US dollar. Each time series represents fluctuations in a different currency pair. The challenge is how to effectively analyze patterns across many correlated currencies without being overwhelmed by the complexity. Principal component analysis offers an elegant solution to this problem. PCA reduces dimensionality while preserving key patterns in the data. It transforms correlated variables into uncorrelated principal components, where the first few components often explain most of the variance. Here we can see how PCA identifies the principal directions of variance in the data. The red line represents the first principal component, capturing the main trend, while the blue line shows the second principal component, orthogonal to the first. Let's see how PCA can be applied to create a currency strength index. First, we analyze the correlation matrix between different currency pairs. Notice the high correlations, indicating redundant information. After applying PCA, we transform these correlated currencies into uncorrelated principal components. The table shows how each currency contributes to the first 2 principal components. We can interpret these components meaningfully. The first principal component represents general currency market movement, explaining 48% of variance. The second component differentiates between commodity and non-commodity currencies, explaining another 29% of variance. PCA offers several key benefits in financial analysis. It reduces noise by filtering out random market fluctuations. It simplifies analysis by condensing many variables into a few components. It enables the creation of composite market indicators, and it improves risk management by identifying the main drivers of market movements. Just as we can see distinct patterns in this penguin dataset with multiple variables, PCA helps financial analysts uncover hidden relationships in complex market data, making it easier to identify trends and make informed decisions. In this case study, we'll examine how principal component analysis can reveal the relationship between alcohol consumption and various health metrics across 10 countries. Our dataset contains information about different types of alcohol consumption and health metrics across 10 countries. We're looking at variables such as wine, beer, and spirits consumption, along with health indicators like life expectancy and disease rates. Before applying PCA, we examine the correlation matrix to understand relationships between variables. We can observe strong correlations, such as a positive relationship between spirits consumption and liver disease, and a negative correlation between life expectancy and heart disease. When we apply PCA to our dataset, we first examine the eigenvalues and the proportion of variance explained by each principal component. The first 2 components explain about 75% of the total variance, indicating they capture most of the information in our data. Examining the component loadings helps us interpret what each principal component represents. The first component contrasts wine consumption and life expectancy against spirits consumption and disease rates. The second component mainly represents beer consumption and liver disease. When we plot countries in the principal component space, we can identify clear patterns. Mediterranean countries like France, Italy, and Spain cluster together with high wine consumption and life expectancy. Russia stands out with high spirits consumption and lower life expectancy. The PCA results have important implications for public health policy. Mediterranean consumption patterns with moderate wine intake appear associated with better health outcomes. High spirits consumption strongly correlates with reduced life expectancy. Beer consumption shows mixed effects. These patterns suggest that culturally appropriate intervention strategies may be more effective than one-size-fits-all approaches. Exploratory factor analysis has proven valuable in manufacturing contexts. This case study examines how EFA transformed operations at a textile manufacturing facility. The textile manufacturing process involves multiple stages from raw material procurement to finished fabric production. Each stage introduces variables that can affect product quality and production efficiency. Before implementing EFA, the facility faced several challenges: inconsistent product quality, production bottlenecks, high defect rates, and declining overall efficiency. Performance indicators were showing concerning trends. These challenges occurred against a backdrop of declining growth in the textile industry overall, putting additional pressure on manufacturers to optimize operations. To address these challenges, the facility implemented exploratory factor analysis. They collected data on 25 production variables, performed correlation analysis, and applied EFA to identify underlying factors. The analysis extracted 5 key factors that explained 78% of the variance in production outcomes. The factor analysis diagram shows how the 25 measured variables loaded onto 5 principal factors. The thickness of each line represents the strength of the relationship between variables and factors. The 5 key factors identified were machine calibration, raw material quality, process temperature, staff training level, and maintenance frequency. These factors became the focus of the improvement initiative. Based on the EFA results, the facility implemented targeted strategies for each key factor, redesigning machine calibration protocols, improving raw material quality control, optimizing process temperatures, enhancing staff training, and implementing predictive maintenance. The results were significant. After implementing changes based on the EFA findings, the facility saw dramatic improvements across all key performance indicators. Most notably, overall production efficiency improved by 25%, while defect rates decreased by 62%. These improvements translated directly to higher product quality and lower costs. The key takeaways from this case study demonstrate how EFA can transform manufacturing operations by identifying the most important factors affecting production. This data-driven approach allowed for targeted improvements that significantly enhanced both efficiency and product quality. Confirmatory factor analysis is a powerful statistical approach for developing and refining measurement instruments. Unlike exploratory approaches, CFA allows researchers to test specific hypotheses about the relationship between observed variables and their underlying constructs. CFA serves several critical functions in measurement development, including assessing construct validity, identifying method effects, evaluating factor invariance across different groups, and testing measurement equivalence over time. The first key application is assessing construct validity, which ensures that an instrument actually measures what it claims to measure. CFA helps evaluate different types of validity. Convergent validity confirms that items measuring the same construct correlate highly. Discriminant validity ensures constructs are distinguishable from related constructs. Face validity verifies that items appear to measure what they claim to. For example, we can assess convergent validity using average variance extracted, which should exceed 0.5 for good convergent validity. The second important application is identifying method effects, which occur when variance in responses is due to the measurement method rather than the construct being measured. A common method effect occurs with item wording. For example, in a life satisfaction scale, positively and negatively worded items might load on separate factors due to their wording, rather than measuring different constructs. The third key application is evaluating factor invariance, which tests whether measurement instruments function the same way across different groups or time points. CFA helps establish different levels of measurement invariance. These include configural invariance, which tests for the same pattern of factor loadings, metric invariance for equal factor loadings, scalar invariance for equal intercepts, and strict invariance for equal residual variances. Let's look at a practical example of using CFA to test a measurement instrument. Here's a model testing whether an anxiety scale functions the same way for males and females. In summary, CFA offers numerous benefits for developing and refining measurement instruments. It provides statistical evidence for instrument quality, allows for precise targeting of problematic items, supports cross-cultural and longitudinal research, enables comparison of different theoretical models, and enhances the validity and reliability of research findings. Crime data analysts face a significant challenge, managing datasets with numerous variables. These variables include different types of crimes, geographical locations, timing factors, and demographic information. Principal Component Analysis, or PCA, offers a powerful solution to this dimensionality challenge. PCA reduces many crime variables to a smaller set of principal components while preserving the important patterns in the data. This creates composite measures of crime intensity and helps visualize complex patterns. Before applying PCA, crime analysts typically work with raw data showing individual incidents. Here's a heat map of burglaries, where each black dot represents a separate crime. While this visualization is useful, it can be challenging to identify broader patterns, especially when analyzing multiple crime types simultaneously. PCA transforms raw crime data into a more manageable form through a systematic process. It creates a feedback loop where data analysis informs intelligence, which then guides decision-making by law enforcement. After applying PCA, we get a simplified representation that combines multiple crime variables into a single crime index. This map shows auto theft rates by police beat integrated with land use data. Notice how PCA has transformed the raw data into a more usable form, highlighting areas with higher crime rates through larger blue circles. This allows police to better understand the relationship between land use and crime patterns. PCA also allows us to visualize the relationships between different aspects of crime. While this example shows flavor profiles, the same approach applies to crime data, where the first two principal components might represent factors like property crime intensity and violent crime prevalence. PCA provides numerous benefits for law enforcement agencies. It helps identify crime hotspots across multiple crime types and allows for more effective resource allocation to high-risk areas. Agencies can predict emerging crime patterns using fewer variables, develop targeted prevention strategies, and communicate complex data to stakeholders more effectively. In essence, PCA transforms complex crime data into actionable insights that drive strategic decisions in law enforcement. When conducting exploratory factor analysis, a critical decision is determining how many factors to retain. Factor selection in EFA relies on two main types of criteria: statistical criteria and theoretical criteria. Statistical criteria include the Kaiser criterion, which retains factors with eigenvalues greater than 1, scree plot analysis, parallel analysis, and percentage of variance explained. Theoretical criteria focus on your research framework, factor interpretability, simple structure, and factor stability. The best approach combines both statistical and theoretical considerations to make an informed decision. The Kaiser criterion suggests retaining factors with eigenvalues greater than 1. This eigenvalue table shows the variance explained by each factor. Factors with eigenvalues greater than 1 explain more variance than a single variable would. The scree plot shows eigenvalues plotted against the factor number. Look for the elbow point where values begin to level off. Parallel analysis compares your actual data against randomly generated data. Generally, you should retain factors whose eigenvalues are greater than those generated by random data. Factor stability is crucial in deciding which factors to retain. A factor with fewer than 3 items is generally weak and unstable. In contrast, 5 or more items with strong loadings of 0.50 or better indicate a solid, stable factor. Remember these key rules. Factors with fewer than 3 items are typically weak and unstable. Look for factors with at least 5 items loading at 0.50 or higher for solid factors. When making your final decision about how many factors to retain, follow a systematic process. First, examine multiple statistical criteria rather than relying on just one. Second, consider your theoretical expectations. Third, evaluate whether each factor can be meaningfully interpreted. Finally, assess factor stability in terms of the number of items and their loading strengths. Throughout this process, ensure you're using the appropriate statistical tests for your data type. This chart shows how test selection depends on measurement scales and study design. Factor analysis is complex, and the optimal solution often requires balancing statistical evidence with theoretical soundness. To summarize, when selecting factors in EFA, use multiple statistical criteria, including eigenvalues, scree plots, and parallel analysis. Balance statistical evidence with theoretical considerations. Aim for strong factors with at least 5 items loading at 0.50 or higher. Avoid weak factors with fewer than 3 items, and ensure your factors can be meaningfully interpreted within your research context. In this final technical section, we'll see how principal component analysis, exploratory factor analysis, and confirmatory factor analysis work together as complementary tools. The choice between these techniques depends on your research question and prior knowledge. This decision tree illustrates how you might select the appropriate method for your specific situation. Each method answers a different research question. PCA helps identify primary dimensions of variation. EFA discovers potential underlying factors when your theoretical foundation is limited. CFA tests whether your data fits a specific measurement model based on theory. These methods often represent a progression in research. You might start with PCA for purely exploratory data reduction, then move to EFA to uncover potential latent factors, and finally use CFA to test and confirm your measurement model. When using these statistical techniques, ethical considerations are paramount. Researchers must be careful not to manipulate analyses to achieve desired outcomes, and should report their methodological decisions transparently. Ethical use includes being transparent about analytical decisions, avoiding p-hacking or fishing for results, validating findings across different samples, and reporting all relevant statistics and fit indices. To summarize, PCA, EFA, and CFA are complementary tools that serve different research purposes. The choice between them depends on your research question and prior theoretical knowledge. Remember to use these powerful statistical techniques thoughtfully and ethically to advance knowledge in your field.